from Princeton University. Professor is one of the world's leading applied mathematicians, so we are especially glad that he agreed to speak today. His work on numerical methods for PDE, analysis for PDE, multi-scale problems, stochastic ODEs and PDEs, rare event analysis, and more recently in machine learning and the interface between machine learning and scientific computing is well known to everyone. So I don't need to speak more about it. Professor has received numerous awards. I can mention the Collatz Prize. I can mention Theodor von Karman Prize. Also very recently, the Peter Henrici Prize from SIAM and ETH. So we are again very pleased that you agreed to speak today. Weinan is going to speak today about PDE problems that arise from machine learning, which is extremely relevant to the journal as well as to this webinar. So Weinan, the floor is yours.
Thank you, Seth. Thank you very much for the introduction. So this topic I've not really discussed much before, but I think it's a very important topic both for PDE and for machine learning. Can you hear me?
We just have to mute everyone. Jan? Yeah. I think it's okay, Weinan.
Okay, so I want to discuss two topics. One is sort of a new regularity theory is needed that for understanding high-dimensional PDEs. The fact that machine learning has made it possible to solve very, very high-dimensional PDEs that demands new regularity theory for understanding what's going on. The second is PDE problems that arise from machine learning. So we want to formulate machine learning in a better way, and that naturally leads to some PDE problems. So let me start about asking the question, what is really machine learning? So that's tough to explain, but in very simple words, here's what machine learning is about. The basic problems in machine learning. So we're given a set of data, where the the values, which are called labels in machine learning, is given by some unknown function f star, called target function. And your task is to do the best you can to approximate this function f star, say using neural network functions. So this is an example of what we call two-layer neural networks, these kind of functions. Two layers because they're coefficients aj and wj. So these are two layers of coefficients. So this is the simplest example of a neural network. Nowadays, people don't use two-layer neural networks very much. They use multi-layers, which means you take functions of this type and you compose many times. Now in this function, there is a scalar nonlinear function, sigma, and that sigma, that's called activation function. So this function can be, is the only nonlinearity, is only where that nonlinearity enters in this expression. Without sigma, this will be linear. And if you compose many times, it's still linear. So with sigma, the function class becomes much richer. Now, a typical choice of sigma is this, what is called ReLU function. This is arguably the most linear function among nonlinear functions. Okay, so this is sort of the basic task in machine learning. So I can sort of, there are many different kind of tasks. So I can say that in summary, machine learning is just a set of models and algorithms for approximating functions. But because we can approximate functions, we can also try to approximate probability distributions, dynamical systems, and solutions of differential or difference equations. Now, so this much is about general approximation, but what makes machine learning particularly attractive, neural network models, what makes them particularly attractive is that they're very effective in high dimensions. So in high dimensions, we know that polynomials don't work because they're just, too many monomials in a polynomial degree p, say, when p is large in high dimension. But neural networks supplies as a very good replacement for polynomials in high dimensions. So if you haven't heard about neural networks, for now, just think about them as some version of polynomials, some replacement of polynomials that's particularly effective in high dimension. Okay, so this, now let me give you some well-known examples that if you're first time seeing machine learning, These are the things that people talk about. The wonders that machine learning can do. This is an example where we're trying to classify images. You are given these images, you try to classify them into categories. For example, these images like airplanes, cats and dogs, and stuff like that. So this is an image classification problem. This data set is called CIFA-10. It's a Weinan data set. But from a mathematical term, this is approximating a very high dimensional function, because each image is defined as a point in this dimensional space, 3,772 dimensional space, because each image is 32 by 32 pixels, and there is 3 dimensions in color space. So we're looking for a function that's defined on this hypercube and maps to 10 categories. So this is a discrete value function on a 3,000 dimensional space. The second example I want to give you is these images, these pictures of people. Now, these pictures share one thing in common, is that they're all fake. They're not real people. They're manufactured by machine learning techniques. And so you can think of this as sampling a probability distribution. The probability distribution here is the distribution of all human faces. So we don't know that probability distribution, but still with machine learning, we can sample that probability distribution and produce these fake pictures that looks very real. So this is a second example. This is sampling unknown high dimensional distribution. The third example is AlphaGo. So you all heard about AlphaGo, but let me just say one thing, that for Go, the best, giving your opponent, the best strategy obeys some Bellman-like equations. So this is the difference equation in a huge space. So if you're looking for optimal strategy for the Go, you're trying to solve some Bellman equation. So all 3 examples are very well-known examples, but behind each one of these examples, there is a very deep mathematical question. So these are the kind of things we want to understand and we want to address. So let me talk about classical viewpoint of regularity. So regularity is a big issue in PDEs. So what do we think about, how do we think about regularity classically? Well, as a numerical analyst, I think of regularity from the viewpoint of approximation theory. So regularity is just a measure of the complexity when we approximate some target function using simple functions, for example, piecewise polynomial functions. So here is a sort of a meta theorem. Suppose let VH be the space of continuous piecewise linear functions over some sort of a regular grid. Okay, well, maybe I shouldn't say linear, maybe some piecewise polynomial, high order polynomial functions. Now, a function U star can be approximated by by piecewise polynomials to an order of accuracy alpha, if and only if that function U star is in the corresponding sublevel space. Okay, so this is the kind of a classical approximation theorem, which says that the regularity of a function measured in sublevel space or Bessel spaces is tied with the rate with which you can approximate these functions by piecewise polynomials. Okay, so this here, I think of this as a complexity because you ask how many degrees of freedom we need. Well, let that be m. The degrees of freedom we need to approximate the function to some error epsilon is given by this formula here, expression. So epsilon to the minus d over alpha. So here there's d as alpha. First of all, alpha is a regularity. So the bigger the alpha, the easier it is. The smaller the value of m is required to approximate U star. So with this, classical theory for PDEs is about whether a function or whether a solution belongs to some sublevel Bessel or C alpha kind of a space. And for numerical algorithms like finite element and finite difference, what we want to do is to establish convergence rates, things like this. And this convergence rate depends on 2 things. One is the order of the method, order of the scheme, second order, first order. And the second is the regularity of the solution. So this is the classical picture. Now this picture doesn't work in high dimension due to the fact that there is this exponent, there is this d-dependence on exponent. So the number of parameters needed scales like this. Let's take the situation where alpha is equal to 1 and epsilon is 0.1. Then m scales like 10 to the d. So if d is like 3,000 dimension, which is not very high dimension by machine learning standards, you would be really, in deep trouble. 10 to the 3,000, that's a huge number. So this suggests, and there are increasing evidence supporting the statement that, classical regularity theory, like Sobolev, Besov, Lipschitz regularity, or C alpha, these kind of regularity do not work well in high dimensions because these function classes are just too large, too big. And secondly, it's well known within the numerical analysis community that grid-based algorithms such as finite difference or finite elements don't work well in high dimension. So essentially, that's why we are stuck with 3 dimensions, and even 3 dimensions can be sometimes hard. So if you want to solve PDE in 100,000, tens of thousands of dimensions, what can we do? This is where machine learning can help. And these are the first 3 papers that started this, and started with the first paper where we looked at control problems in high dimension. The second and third paper will look at PDE problems in high dimension. Let me give you one example. So let's look at this nonlinear parabolic PDE. So I'm formulating this as a terminal value problem, thinking about applications to finance, formulated as a terminal value problem. Suppose we want to solve this PDE in 100 dimension. So that's what we did in these papers. So how do we do that? Well, we want to use machine learning. If you want to do machine learning, as I'll remark later, the first task is to formulate the PDE problem as a stochastic optimization problem, meaning that we want to formulate PDE problem as minimizing some expectations. So this problem, I claim, can be equivalently formulated as follows. You minimize the match between the solutions of this stochastic process, which is called backwards stochastic differential equations. You minimize the value of y with the terminal value g, subject to the fact that these guys satisfy this BSDE. The curious thing about this BSDE is that even though there's only 2 equations, 3 unknowns, x, y, and z are all unknowns, there is only a unique solution that's adapted in the language of SDEs. There's a unique solution. As a matter of fact, that unique solution is also given by the solutions of this PDE via these formula. So that's just the mathematical equivalent formulation. Now we're going to use this equivalent formulation to formulate a numerical algorithm, deep learning. First step is discretize in time. So discretize these guys in time. This is using standard Euler discretization. After discretizing time, we're going to define these relationships. We're going to approximate these relationships. One is this, which would be the initial value of y. And then the other is these z's, that's represented here. Sorry, why doesn't work? We represent here. We're going to approximate these function dependence, these functions, by some neural network functions. So never mind how we do that, but suppose we have done that. Then what we have done then is that given any realization of the noise, remember the stochastic differential equation depending on the Weinan noise, given the formulation, realization of the noise, we have constructed a function that maps this noise to the terminal values, that yt. And then we minimize the difference in order to find the optimal parameters in this neural network function, the fitting parameters in this neural network function. So this is the algorithm that we formulated back in 2017. And it works out very well, turns out. Let me give you some examples. You can look at the papers for more details, but I'm going to look not so much about it. So let's look at this stochastic control problem. This is called linear quadratic Gaussian. So it's a linear problem with control MT, and we want to minimize this cost function. There's a running cost, there's a terminal cost that defines the terminal value. The solution, the Hamilton-Jacobi-Bellman equation is just this equation. If you look at this equation, here is the Euclidean norm. This is just high-dimensional versions of the Hamilton-Jacobi equation. There is a Hopf-Kohl transformation that gives you the solution expressed in this form. So we can use this Hopf-Kohl solution to find the exact solution. And this is, you know, the comparison between the method that I just described in the previous page and the solution that obtained from sampling of this expression. So you can see that, you know, the error is reasonably small. You can refine by doing, you know, refine the neural network, refine the discretization, all that stuff. So that's one example. The second example is an example of a nonlinear Black-Scholes equation. So I think the last speaker was Anna Jensen. So unfortunately, I couldn't come to that talk, but I presume that he talked about this too. He's a collaborator on this work. So, well, he's a collaborator on many of the work I discussed. So this is a nonlinear version of Black-Scholes, where this is sort of, you can imagine this, you know, model some nonlinear effects. And you can see that these, you know, this is the solution of this Black-Scholes equation at one particular value as, and compare one particular value, and these shaded area. So this is actually the solution you would get as you train the neural network. When you do stochastic gradient descent to train a neural network, the prediction of the value of the solution U at time at x equal to 0, say, you know, converges to some limiting value, and this limiting value has good accuracy that you can calibrate. So this has already been used by banks to do, you know, option pricing and stuff like that. So okay, so the fact that these very high dimensional PDEs can be solved means that their solutions cannot be very complicated. So these are functions of, you know, 100,000 dimensions. So they cannot be very complicated. They must have low complexity. So how do we characterize this low complexity? So this is the question, the first question I want to discuss. Well, the intuitive answer is that they can be approximated easily, say by neural networks. The question is, how do we quantify this, this ease? So so one way to do this is just to compute the computational complexity. So that's what we did before. If you want to compute the solution to some error tolerance epsilon, what is the complexity required? So this kind of question has been addressed in one context. This is almost the only example that I know of. So here, take the nonlinear heat equation. We want to solve this nonlinear heat equation in high dimension. This is hypercube in d dimension. Well, let's formulate this as a fixed point problem. That's easy. And we write this fixed point problem and as u equal to psi of u. And then we formulate the Picard iteration. That's also easy. Next, we write this Picard iteration as a telescope sum. So this way. Now, the next step is quite important, although in Monte Carlo it's known before. Namely, now, each one of these phi's is an expectation. So we're going to do Monte Carlo. In high dimension, Monte Carlo is the thing to do. So we're going to do Monte Carlo. But the key thing is we're going to do Monte Carlo with different accuracy. So as n becomes bigger, these terms are less important. So we're going to sample them with less samples. As a matter of fact, we're going to decrease the number of samples geometrically. So this is what we call multi-level Picard iteration. And this is an algorithm developed by these group of people. And we also succeeded to show that the complexity required in order to reduce error to epsilon scales like d. So linear in d and epsilon to the -4. So this is a statement about the complexity of the algorithm. But I want to say that this is also a statement about the complexity of the solution. But ideally, we want to answer this question not just in one shot, like here, you know, to tell you the complexity right away. We want to address this question in two parts. Namely, we want to first develop a general approximation theory for functions. And then we do a regularity theory for PDEs, for solutions of PDEs. Remember, this is how we did in classical numerical analysis or classical PDE. The first part would be to say, okay, for functions u star, let me back up. So given a hypothesis space, so a space of functions. So machine learning is called hypothesis space. Think of them as just these two-layer neural networks with M neurons. The sum has M terms with M neurons. So given a hypothesis space, a sequence of hypothesis space, and given a target function U star. So we want to say that U star can be approximated by functions in that hypothesis space to a certain accuracy, if and only if that there's some norms, some norm-like quantities, gamma alpha is finite. So we want to say that's true. And we want this alpha to be independent of dimension. So that's the key. So we want to ask, what is this gamma alpha? So first of all, is this true? Can this be true? And if this is true, what is the value of alpha? And then what is this norm-like thing, gamma alpha? So this will be sort of approximation theory, analog approximation theory in high dimension. And then the second part will be, given a PDE, like these nonlinear heat equations, are the solutions of that PDE, do they satisfy? Do they satisfy their gamma alpha norm? Is that finite? So we want to answer the question in two parts. So let me just now give you some flavor of what has been achieved. The short summary is that, so in this part, the first part, we have made reasonable progress. In the second part, there's not much, although I don't think that's so terribly hard, but there's not much that's been done. Okay, so let me first address the question, what is the value of alpha? If this is true, what would be the value of alpha? Well, as you probably would expect easily, that alpha should be half. Alpha should be half. Why? Well, this is suggested by Monte Carlo. So suppose we want to compute this expectation, and we want to approximate the expectation by this sum, and let xj to be ID samples of this probability distribution mean. And this is a straightforward identity, which says that the error squared, the variance of the error, scales like 1/m. So, alpha would be like a half. So this is sort of the gold standards for looking at functions or looking at things in high dimension. Monte Carlo is sort of the gold standards. What we want to do is to do the same thing, to try to do the same thing for a functional approximation, which is the one level higher. Here we're just computing one quantity. Here we're approximating the whole function. So we want to say the same thing. So we're, alpha is half, which means, since this is squared, this exponent is 1. So the question would be that first of all, is this true? For what kind of hypothesis spaces that this is true? For piecewise polynomials, this is not going to be true. We know that this is not true. So for what kind of hypothesis space, say neural networks, is this true? And if it's true, what would be this norm, gamma of f star? Notice I put norm in quotation marks. So this is the next question we want to address. First, let's look at this linear model, which is called random feature model. So what is a random feature model? So let phi be a collection of features. We call them random features because these features are parameterized by a random variable w, and pi is the distribution of that random variable w. So pi, wj is just an ID sample of pi, and then we can formulate this hypothesis space, which is just linear combinations of these phi at these values of wj. So then for functions of this form, which if you notice, is just as a continuous formula, continuous limit kind of these kinds of expression, we can define a norm that's this. By the way, I should have added an infimum here in principle because this actually here maybe not so. Anyway, we can define these kind of norm. And in particular, if p is equal to 2, then this norm is nothing but the norm in the well-known reproducing kernel Hilbert space with this particular kernel. But I want p, general p. So this is going to be our gamma of f. So why is that the right quantity? Because for this quantity, we can prove direct and inverse approximation theorems. So for example, if say the norm, f infinity norm is finite, then you can approximate the function f by, this is the L2 norm, by the random feature models with these kind of accuracy. So this kind of a statement is standard in machine learning. Namely, you have to say that for any value of delta with probability of 1 minus delta, that this is true, and there are logarithmic terms in delta. And this is because somewhere along the way, there's always some sort of a concentration inequality involved. So this is a standard. So that's the direct approximation, except for the logarithmic terms. It's exactly the same as the kind of theorems you would see in Sobolev approximation theory, classical approximation theory, except these guys replace Sobolev spaces. And here we just have m, not like m to the alpha. There's no like order of accuracy. And there's also the inverse approximation theorem, which says that if a function can be approximated by these random feature models, and the coefficients are uniformly bounded, then this function must be in the right space. Namely, it must admit such a representation, and the f infinity norm must be finite. So these are the kinds of like approximation theorems in high dimension that we're looking for. Second example, two-layer neural networks. So this is the two-layer neural networks that we discussed before. And these are the parameters. So now I want to ask, for this kind of hypothesis space, what will be the right function space associated with it? What will be the analog of gamma, the function gamma, the norm? The answer is the following. We have to consider functions of this type. So again, this is like continuous form of these guys. We have to consider functions of this type. And these functions are natural expectations. That's what's important. So rho here is the probability distribution. So these functions are natural expectations. And for functions of this type, we can define a norm this way by taking, these kinds of quantity, which is like, almost like, L2 over the parameter space, over the weighted parameter space weighted by rho, and infimo over all possible rows such that this is true. So this kind of, we call this norm Barron norm, to honor the many contributions of, Andrew Barron. And this is, if a function is continuous and Barron norm is finite, we call that a Barron function, and we define this as a Barron space. So the idea here is that the Barron space replaces the reproducing kernel Hilbert space for two-layer neural networks. So the reason we say that is that, again, we have both direct and inverse approximation theorem. If a Barron norm is finite, then the function can be approximated by two-layer neural networks with this kind of accuracy. Conversely, if a function can be approximated by two-layer neural networks, where with the coefficients being bounded, then that function has to be in the Barron space, and the Barron norm has to be finite. So similar theorems are also being proved for residual networks. So this is really the very most effective, really deep neural networks and multi-layered neural networks. Except that for multi-layered neural networks, we're not able to prove, sharp estimates, Monte Carlo kind of rates. So this rate is worse than Monte Carlo. So these are sort of the approximation theory. So the next question is, what about regularity theory for PD? So so far we've said, if your function is in the right space, or if the right norm is finite, then that function can be approximated by the corresponding machine learning model, neural network models or random feature model to Monte Carlo accuracy. That's what we've said so far. So now we want to ask the question, given a PD, is the solution of that PD in these spaces? And we don't have any result of this type. The closest that I can find is the theorem proved by Arnulf Jensen and the collaborators, which basically says the following. So there's a lot to read about this theorem, but let me summarize for you. So consider these nonlinear heat equations, satisfying these, nonlinearity satisfies, certain standard regularity requirements and growth condition requirements. The important thing to say is that if the initial condition can be approximated by neural networks to some sort of complexity. So P is the number of parameters in that neural network. So if that P scales, at most algebraically, epsilon is the accuracy requirement. So if the initial condition can be approximated by neural networks with this kind of a complexity, then the solution of the PDE can also be approximated by neural networks with a different exponent eta. So these are the kinds of things that have been proved. But there are no theorems stating that the PDE solutions of the PDE belongs to these kind of spaces identified earlier: Barron space, representing kernel Hilbert space, flow induced space, induced space, etc. So that's the first part. Let me see how much. Oh, I need to speed up. 12 minutes left. So the second part, so first part is about high dimensional PDEs. Second part is about PDEs that from continuous formulation of machine learning. So why do we talk about continuous formulation of machine learning? Machine learning has two very distinctive features. One is that they're very powerful. We are very convinced of that. I'll show examples of that in the beginning of the talk. The second feature of machine learning is that it's also very fragile. You have to be very good at tuning the models, tuning the parameters and stuff like that. If you are not very good at it, you may not be able to produce good results. It's very fragile. So it's almost as if that we are solving an ill-posed problem. So as a PDE person, we want to have well-posed problems. So now we naturally want to ask a question, can we formulate sort of well-posed formulations of machine learning? Of course, that's a very big question because we don't know, there's no corresponding notion of well-posedness for machine learning, but that's sort of the strategy, that's sort of the basic idea. So suppose we want to do that, what are the key ingredients? So these are the key ingredients, there's three. One is that we have to figure out a representation of functions, and we have to represent functions as expectations. So for example, this is the usual Fourier representation. This is not an expectation. So we don't like that. We prefer this one. The only change is that we replace d omega by pi of d omega, where pi is a probability distribution. In this form, f is expressed as an expectation. So this is much better. So in machine learning, one thing we've learned in machine learning is that we have to think about the functions as expectations. So that's one ingredient. The second ingredient is that, at the end of the day, machine learning is some optimization problem, or variational problem. So we want that variational problem to be formulated as an expectation too, what's called stochastic variation. And the third component is how do we solve these variation problems, gradient flows. So let me discuss, point 1 and 3. 2 is kind of, I'll skip 2. For the supervised learning, 2 is trivial because we just want to minimize the population risk, which is like an L2 norm of the error. So let's look at representing functions as expectations. So this is the kind of a representation that we have already looked at, as a matter of fact. If you remember the Barron space, that's how we define Barron space, except I used to use, I was talking about this formulation. But we could also write this equivalent as this, where pi will be the marginal of rho on W. Or we can have more general versions, not just a sigma WT, this type of functions, but general feature functions like, general functions phi. Okay, so this is the kind of formulation we already discussed, particularly in connection with two-layer neural networks. And so that's one way to formulate functions as representations. Another way to formulate functions as representations is to continue to consider this ODE, where the right-hand side of the ODE is these kinds of, transform-based representation. And once you solve the ODE to time 1, and you can just, this is going to be a vector, and ODE defines maps. This is going to be a vector. We just contract all the components and make a function out of it. So here the parameters will be, say this function A, or this probability this function A, or the probability distribution pi, or the probability distribution rho. So here, the parameters will be these one parameter family of probability distributions pi, or probability distributions rho, etc. So we want to optimize these parameters in order to fit some function. Okay, so this is the kind of approximation. So now how do you optimize? We can, if you go back to, if we just think about supervised learning, we just optimize these kind of, this kind of functional, which is called population risk in machine learning. This is our ultimate goal. So we want to choose the optimal parameter theta so that this error is minimized. So how do we define gradient flows, or different versions of gradient flows for that task? Well, let's draw some inspiration from statistical physics. There's a very well-known paper by Harper and Holmberg, in which they say, okay, if you think about these parameters, there are two different kinds of parameters. This parameter pi, because of the probability distribution, the total integral has to be 1. So when we define gradient flows, that gradient flow has to be conservative. How do we define conservative gradient flows? Here is the recipe. First, you define variational derivative, the standard L2 variational derivative. And in physical terms, this is called chemical potential. With the chemical potential, we can define the velocity. This is called Fick's law. With Fick's law, you can write down the continuity equation. And this is the gradient flow. This is the gradient flow is also the gradient flow under the Wasserstein metric. It's just, this is the physicist's way to think about it. Wasserstein metric is the mathematician's way to think about it, but they're the same thing. But if you look at this parameter A, it doesn't have to be conserved. So we can just define this sort of straightforward L2 gradient flow. So let me give you, so this is the continuous formulation, and then we just discretize. We discretize everything in sight. We discretize the population risk by replacing the expectation by finite sums using the data. That's called empirical risk. And it would discretize its PDEs using standard numerical methods. This would be a numerical analysis way of thinking about machine learning. Now, when we discretize, especially when we discretize the gradient flow, there are finite difference. You can think of finite difference, finite element, but we all know these guys don't work so well in high dimension. The one numerical method that works in high dimension is particle method, because that's nothing but the dynamic analog of machine learning, of Monte Carlo. And I want to show you that actually this strategy I just suggested will produce the standard algorithms in machine learning. So let's look at this sort of integral transform based representation. This is the integral transform. In that case, let's take rho as being the parameter, and that's the conservative because that's a probability distribution. In that case, the flow is, model B flow is this guy, the Wasserstein flow. And this, by the way, is the same thing as the equations produced by these mean field viewpoint. So there's several independent papers, very, very good papers written 2 years ago that proposed the mean field approach to training 2-layer neural networks. And in the mean field limit, they produced the equation, which is exactly this equation. So now we want to discretize this equation. So how do you do that? Using particle method. Well, particle method means we're going to replace this probability distribution by some empirical distribution centered on some particles. These particles, AJ and WJ, let's call that UJ. And the dynamics of the particles is going to be given by this, from this equation. And the claim is that in this case, the solution rho is also an empirical distribution. And then with the UJ evolved, by this gradient descent flow of a function which is exactly the same function as the population risk. So the gradient descent dynamics in 2-layer neural networks is the same as the continuous flow that we just formulated. Now, about this continuous flow, you would ask, what are the mathematical results that's known? Not very much. The one most important result, I would say, is the following. So before I say that, let me make an important remark, which is that this Wasserstein gradient flow is not a very nice flow. So for gradient flows, standard gradient flows, like these guys, the nice situation is that when this function now is convex. For Wasserstein flows, we want it to be displacement convex. If the functional is displacement convex, then everything is nice. Then we can prove lots of theorems, convergence rates and stuff like that. Unfortunately, these functionals are not displacement convex. It's very hard to make them displacement convex. So that makes a lot of these machineries in optimal transport theory not immediately applicable. But there's one non-trivial result that's been proved first by Josette Bach, and more recently my postdoc Wojtowski improved upon this. The theorem basically says the following: if the initial condition is has full support, let's say has full support, okay, support covers everywhere. Let's say, the exact condition is formulated here, but let's just say, let's assume initial condition has a nice density, and the density has full support, and let's assume that the velocity potential converge. Then we can show that the limit has to converge to a zero. That means the population risk has to go to zero. So this is saying that assuming convergence, then the limit has to be zero. It has to converge to the global minimum. The good thing about this, the bad thing about this, you have to assume convergence. The good thing about this is that it actually reveals something that's important in practice, namely the initial condition. It makes a difference whether your initial condition has full support or not. So in one dimension, one-dimensional analog, there's more that's known. So in one dimension, let's consider, on the circle with periodic boundary condition, and then this differential equation becomes this form, where the kernel is given here, and we'll consider, target function of this type. So there's one theorem that proved by, my students, myself. Oh, I have to stop. Sorry. Let me continue for 1 minute. 2 minutes.
You can take 5 minutes if you want, Weinan. You started 5 minutes late.
Oh, good. That's very nice of you.
Yes,
Okay.
take your time.
Okay. So it says that if your target function has uniform distribution, so this is a very special case, rho star is uniform, then there's nice convergence. Okay, that's because in this particular case, that this entropy is a Lyapunov function. So this is a very special case. It's one dimension. It's when rho star is uniform. The second theorem is a local theorem, which says that it's still in one dimension. It basically says that if your initial condition is close enough to the target distribution, this target distribution doesn't have to be uniform distribution, then your solution will converge with 1/t kind of a convergence rate. Okay, so this is proved by constructing invariant regions. So it's more general target distribution, but it's local. And again, it's 1D. So these, I've given you all I know about this, this PDE, these kind of PDEs. I personally feel that these kind of PDEs and the one I'm going to discuss for the dynamic system formulation are really going to be very fundamental PDEs, just like Navier-Stokes. So let me now discuss the flow version of these PDEs. So we're going to, this is the machine learning from a dynamic system viewpoint. We're learning functions by the help of ODEs. So let's consider more general form. I'm going to consider these kind of ODEs where general features and the parameters of family of probability distributions rho tau. And we want to minimize this population risk by choosing the parameters rho tau. So rho tau is a family of probability distributions. So this is the optimal control problem. In optimal control, we have the maximum principle, contractor maximum principle. To formulate that, we define the Hamiltonian, where it's defined a state space, co-state space, and this parameter space, which here is the probability distribution. And maximum principle, which is essentially, KKT type of condition, says that the optimal row has to be, argmax of this expected Hamiltonian, and the states and co-states satisfy these forward and backward equations. So this is sort of a maximum principle in this particular context. Now, already, this is already a kind of a nice PDE problem. But if I want to make a connection with the kind of PDE I discussed just a minute ago, let me replace this by gradient flow. Replace that by this gradient flow. So now I have a one parameter family of gradient flows for a one parameter family of probability distributions about tau, and they're coupled together by this forward and backward equation. And I claim that this guy is the continuous analog of ResNet. Remember, ResNet, the most popular really deep neural network models. Indeed, if you discretize in the same way as before, if you discretize these guys using the kind of particle method, you recover the standard algorithms for ResNet. But we can do more. We can formulate new algorithms. We don't have to do the gradient flow. We can sort of start with the maximum principle and just formulate an algorithm on this level. So this is an algorithm proposed by Chen-Xiao Li and collaborators, including myself, called method. It's called adapting method of successive approximation from control theory to this context. Turns out you have to sort of modify the Hamiltonian in order to make it really work. And if you look at the performance of the algorithm compared with standard stochastic gradient descent, in terms of iterations, especially when you initialize badly, it really, outperforms the gradient descent SGD type of algorithm, Adam, Adagrad, and stuff like that. Okay, in wall clock is not as impressive because there's a lot of things that we didn't tune. So anyway, let me summarize. If I think of, over the several years, maybe 5 or 6 years I've worked on this machine learning, what have we really learned? Actually, for me, it's really these kind of ways to represent functions, represent as expectations. So these kind of expectations or these kinds of expectations. And these are the most fundamental things. So we have to think about functions this way, in high dimension. Now, if you can figure out a different way of representing functions as expectations, and that different way may give rise to a whole new class of machine learning algorithms. So I can only think of these two general classes, integral transform based and flow, ODE based. And then we can discretize using standard numerical methods, particle methods, spectral methods. Well, then we get, our machine learning model. This allows us to think outside the box neural network models. Okay, so this is what I wanted to say that, first of all, there are new PDE questions. Machine learning itself, gives rise to PDE questions. And if you want to learn more about it, I recommend reading 3 review articles that were written and I posted on my webpage. This one hasn't been posted, but I'll post it next couple of days. This one is about mathematical theory of machine learning. This one is about solving, high dimensional PDEs. This one is about, physical modeling, molecular dynamics, kinetic equations, stuff like that. So thank you very much. I'm sorry that I a little bit went over. I'll stop here. Bye. Sid? Hello? Everybody gone?
Yes, thank you very much, Weinan, for this excellent talk and for this beautiful overview of machine learning and how PDEs enter into machine learning. So we have 5-10 minutes for questions. And as Jan has already said, you can post your questions in chat. Let me see if there are any questions yet, or you can also raise your hands through the raise hand button and ask questions. But so far, I don't see any. Maybe I can start by asking a question and give people the opportunity to ask more questions. So regarding Barron spaces, Weinan, what if I have analytic functions? Are they automatically in a Barron space? Or if I have infinitely differentiable functions, how do you relate classical Sobolev spaces and Bezos spaces to Barron spaces.
If the yeah, there's a result proved by Andrew Barron, which says that if the Fourier transform decays fast enough,
Okay.
First moment is finite, then it's Barron space.
So in particular, solutions of the heat equation with reasonable initial data are in the Barron space then.
That's right.
Okay.
But what we really want to know is that so that's true. So, but we want to know more. We want to bound the Barron norm of the solution by the Barron norm of the initial condition. So
and this is hard. Has this been done in any example?
I don't think so. Even though anybody could do that in a minute. I haven't seen any.
I see. Okay. Questions from the audience, or I don't see any yet. If not, I can ask another question just to give people time. So the question was about this beautiful PDEs, this gradient flow formulation that you had, which was the formulation with respect to the Wasserstein metric that was not displacement convex. Mm-hmm. So maybe I missed it, but was this specific to a two-layer neural network, or this was a very general multi-layer neural network gives you the same PDE? So
that's a very good question. So for two-layer neural network, we have this nice PDE.
Yeah.
Multi-layer neural network, it's difficult to write down PDEs like this, but there's an analog formulation. So that's in the paper by Wojtowski and myself.
I see.
But for deep resonance, it's these guys. So it's these guys.
I see.
So it's a family of these guys, and they're coupled by this forward.
And do you have any is this displacement convex or not at all?
No, this is not displacement either. It's not.
And you don't have any kind of, at least in the pure case, you had this result where if there is convergence, then the residual is 0 or the minimum is 0. Do you have any such results, such conditions?
Okay, so this result is going to be proved any minute now. So I have my postdocs are working on this, and they have some versions already.
I see. Now some people are asking questions, so I can read out the questions. Okay, someone is asking, what is the training set? For neural networks, it is usually required a training set. What is the training set? Means do you understand this question? Means
I guess training set is whatever data you use to train your model.
I presume the question is it a random training set, or anyway, we can take the next one. Any compact continuous function on a compact set can be approximated by an artificial neural network. Anything of this type holds for solutions of PDEs or ODEs?
Yeah, so that's easy to prove. So these universal approximation theorems, they still hold.
Yes, good. Further questions? Yes, no, someone is saying, can I obtain a copy of the slides? I think there will be slides made available, so that's not going to be a problem. Yes, so further questions? Where is the place of the curse of dimensionality in the structure you mentioned in your talk? Again, I leave it to you to interpret it.
Well, the idea, the hope is that if you do classical stuff, piecewise polynomials, so there is curse of dimensionality, that's clear. The hope is that if you do the kind of stuff I formulate later with this continuous formulation, or with the neural network models, there's no curse of dimensionality if the target function is in right space. So we have succeeded in proof sort of part of this, but not all of this yet. And there are issues about whether this is really true, still non-trivial issues.
Good. How many training data do you need to achieve the accuracy? This is from Peng Chen. How many training data do you need to achieve the accuracy you showed with respect to dimension?
Okay, so this is the part that I sort of deliberately skipped. So you remember the first part I talked about approximation theory. So this is approximation error. In machine learning, there's also another error which is called estimation error. That's related to training data. approximation error is related to the size of your model, how many parameters. Estimation error is related to the size of the training set. So there's an analogous kind of issue, analogous theorems that has been proved. So the error scales like 1 over the square root of n, on again Monte Carlo type, where n is the size of the training sample.
Good, thank you very much. Further questions? Someone is asking about, was Duffy the only source for the Black-Scholes equation with default risk?
Sorry?
Was Duffy is a reference that you mentioned with Black-Scholes, right? Was it the only source of Black-Scholes equation with default risk? I don't know this, you have to take it.
I don't know. I mean, we took this equation from Duffy, you know, he solved in, I think, 5 dimensions, and we solved in 100 dimensions. But I'm sure there are other equations of the same type also.
Someone is asking a question about time discretization of the backward stochastic differential equations. There is a time discretization error. Then we have error of the neural network. Is there any analysis on how to choose the parameters such that these are somehow combined?
Okay, so there is an analysis of the this time discretion error. So that's done. That's done by Jiechun Han and Jihao Long. They have a paper. Time discretization is taken care of, but then discretizing with the neural networks, that's not done.
Good. There's a question from Claudia Munoz, who was one of the speakers before in the seminar. In high dimensional PDEs, one has supercritical behavior, namely high possibility of finite time blow up, even in the case of smooth initial data. Do you face that problem in the deep learning, machine learning approximation theory, supercritical behavior?
That's nonlinearity. I would say certainly we could, right? If we attempt to solve that kind of equations by neural networks, we're going to face the same issue, same problem. But I would say that's not the main concern here. So our concern is not about blow up, but rather characterizing complexity.
And in particular, this sort of variational PDEs that you get, they don't show any supercritical behavior, right? You are bound
right. For these PDEs that we proposed, for the PDEs that we proposed, yes, we can show there's no blow up.
Good. I think someone is asking questions about numerical experiments. I'm sure that these are available in your review papers, particularly the one on algorithms.
Yeah, right.
So this is, you've already indicated that. I think if there are no further questions, we are at 4 o'clock European time. So we thank Weinan again, and yes, so Jan, you want to say something or no?
Well, I just said it in chat already. So thanks Weinan, of course, for the very nice talk, and then hope to see many of you again next week, same time, same place, for a talk by Claudia Munoz on soliton dynamics.
Well, thank you, Jan. Thank you, Sid. Thanks for
Thank you very much, Weinan, and have a great
see you sometime, Sid.
Ciao. Yeah, see you sometime.
Bye-bye. Thanks.
Bye.